Good day, mates, right? It's evening in Australia. Well, I don't know if there are some people from other countries. Here it's early morning, so if I start to yawn, don't hold it against me. I'm still kind of warming up. Yeah, thank you for having me, for inviting me. Maybe some of you know that I've been actually in Australia about a month ago at Yao series of events where I did this talk, and so I'm doing a redelivery here. This is a talk which is kind of aimed primarily at people who are new to Elixir. But I still think that you as more experienced Elixorians are going to have going to find something interesting for you, because the bulk of this talk is basically about case studies, about exploring a couple of real-life situations of Beam concurrency in practice, taken from real-life projects I've had the pleasure of working on. And so this is, what's going to be the majority of the talk. But before I start with that, I'm going to do like the traditional, what I typically do, a very quick intro to Beam concurrency. Just to make sure that we're all on the same page, just to make sure we don't lose people in the audience who are maybe new to these languages. And so, yeah, that's basically the agenda. I'm going to do a quick intro to Beam concurrency, and then I'm going to walk you through a couple of examples of its usage in practice. And then we're going to do Q&A. I'm, available for as long as you have some questions. And yeah, roughly the duration should be about 40 minutes or so. I didn't time it, but like that's how it took, or how long it took when I was doing it live in Australia last month. So yeah, basically that's it. Let's kick off. So this talk is focusing on Beam, which is the runtime of languages such as, or of programs written in languages such as Erlang, Elixir, and others. It's kind of like a JVM or CLR for the Erlang ecosystem. And I typically focus in my talks on Beam or on runtime properties. So I typically treat those languages as a kind of an interface to harness the power of Beam, and it's not going to be different in this talk as well, right? So I'm going to use Elixir examples, but because Elixir is my favorite language of the Beam languages, it's the one that ticks the most boxes that I want, but basically it could have been any other of these languages or other Beam languages, right? But just to make sure, when I speak about concurrency, or when I speak about various properties, I focus on Beam or on runtime level properties. So the thing about concurrency in Beam, the central idea here is a thing called process. So this is not an OS process or an OS thread, it's a Beam level concept. And essentially I like to say that process is a sequential program, right? It's just basically a bunch of expression executed one by one sequentially. Every piece of code at runtime runs within some process. It's a runtime context of execution of your code. And from within one process or one sequential program, you can start or spawn additional processes in various different ways. So here I'm using the standard library function from Elixir called spawn. And just an important note, like this is a very low level function, the lowest level abstraction that we have at our disposal. Typically, we don't use that thing in production. We would use some higher level wrappers, which take care of some boilerplate, various edge cases and whatnot. But I'm focusing on the fundamental properties here, and so I'm going to be using these lowest level abstractions throughout this presentation in code snippets, because I believe that this drives the point much more clearly. So yeah, so basically here we have like a sketch of one sequential program. The execution flows from top to bottom, one expression at a time. We invoke spawn, we pass it an anonymous function, and basically this starts another process, another independent sequential program, and the function is running there. And as soon as the process is started, spawn returns, and the caller client program, the starter program, this program here can move on to the next instruction. The result of the spawn function is a thing we call PID. It's a process ID, the piece of data uniquely identifying the process in the system. And once you have the PID, you can interact with this program. You can send it messages, right? Because these processes, they are basically independent programs. They share no memory. And so the primary, if not the only way they can cooperate or work together is by sending themselves messages, which is known as message passing concurrency. So basically, to send a message, you need to have the process ID of the target process, and then the message is an arbitrary piece of data, whichever term you can construct. So you invoke this send, and as a result of that invocation, the message payload is placed into the mailbox of the receiver process, right? So each process has a mailbox, which is basically a FIFO queue associated with it. And so we place the message content into that mailbox, and then the sender process moves on to the next expression. On the receiver side, you can pull one message from the mailbox by using this receive expression, and then you do something with the message. You do your typical conditional logic, some kind of if or case style branching, and you handle the message somehow. And finally, the slide I typically have at my presentations, the runtime picture of the entire thing. So basically, once you start your system, right, you're going to have like some system implemented, organized, your code is going to be organized in some project, and then you're going to start this project using some magical command. What happens is a single operating system process is started. This is your own instance of Beam, where your system is running. And inside the single OS process, you have a bunch of these small programs, these processes, these independent sequential programs, which are the things you spawned on your own. And typically, you're going to have a large number of those things. Like even in smallest programs, easily a few hundred of those processes may be running around. Like if you're using Phoenix Web Framework, just by default, or even Cowboy, the lower level abstraction, the Cowboy web server or the plug with Cowboy adapter, you're going to have like, I think, at least 100 processes out of the box immediately, just for Hello World. So you're going to have like a few hundred processes for smaller programs, medium to large scale systems, easily a few thousands, hundreds of thousands, millions of those things may be running around, because these processes, they're very lightweight. They're very cheap in terms of startup overhead and memory overhead. And so we can really run them in abundance. We can run them in millions. And this is what we typically do. To me, this is the Beam concurrency, the Beam way, or the Beam approach to concurrency, to be highly concurrent. We are not afraid of concurrency because we have like a really good abstraction in our hand and fairly cheap abstraction in our hand, and because there's a lot of potential for concurrency, even in programs or in systems which are not operating on a large scale or which are not that complex, right? And this is perhaps the most important point which I'm trying to drive with this talk. So either way, you're going to have a bunch of these processes running in the single OS process. And behind the scene, internally, Beam is going to use a couple of OS threads called schedulers to actually run those processes, to interpret the compiled code, to spread the execution across available CPU cores, and make your system multi-core capable and vertically scalable. And this is basically it. That's my intro to Beam concurrency. It's not really, there's not a lot of that stuff. Obviously, I didn't give you the full picture. I'm gonna add a couple of more pieces of information down the line, but it's not really all that complex. I actually think it's like surprisingly simple, fairly straightforward to reason about, yet incredibly versatile and powerful. And the aim of this talk is to kind of show a bunch of different examples and different situations where we can use this concurrency and how it can help us get some interesting benefits, right? And how we don't have to be afraid of concurrency, unlike with some other more traditional technologies. So we're going to take a look at a couple of case studies, and I'm going to start like fairly simple for just for warm up with the thing I'm calling like asynchronous execution of a long-running task. It's a sort of generic umbrella term for the scenario, which I think I probably found in like 100% of the systems or backends that I have worked on, regardless of the complexity domain or scale. And it's an example of a situation where you pretty much need concurrency, again, independent of the scale you're operating on. So in the particular scenario that I'm going to discuss, we were building the system which could be described as privacy sensitive data analytics. Right. So the system we were building, basically, our clients, the clients of our product, were companies which had their own product, and people were using that. Their product was like user facing or mass user facing, and the people using those products, as a result of that, there will be some various data gathered in the database, and our clients, those companies, wanted to do the analytics over the database, to gather various insights, to figure out some correlations, usage patterns, and whatnot, without compromising the privacy of individual people, right? So they wanted to open up the database for analytics, but they didn't want to allow the analysts to actually be able to access individual private data from their users. And this is basically where we came into play. Our product comes into play. Basically, our product was deployed on client premises. And it would be sitting in between the analysts and the database itself. And so we would be accepting the analyst queries, like literally our input was a SQL query as standard in text format. And we would be interpreting the query, fetching the data, returning the result of that query, making sure that nothing in this result reveals anything sensitive about any individual, individual person, right? Which sounds like a lot of dark magic, but it's just a bunch of smart post-processing algorithms performed on the fetched data. This would be like a talk in itself. But either way, the whole point is that like running this single query is a time-consuming experience. So because we have to fetch the data and do some intensive smart post-processing of that data, and we're dealing with a larger amount of data. And so easily, even in shorter or quicker scenarios, it could run for a few minutes. It wasn't uncommon for it to run in some cases even well above a single hour, right? So running a single query is a long-running task. And obviously, you want to run this task asynchronously, concurrently to everything else in the system. Because if you run it sequentially, then your entire system is paralyzed until you finish that single query, which doesn't really seem all that useful. Like to have the entire system blocked for everyone for 1 hour, for example. And so this is an example where you need concurrency no matter the scale. Right, so this system here was ultra low scale. Actually, per single installation, we would have a handful of analysts doing a handful of queries daily. This is super low scale, and still there's need for concurrency, right? And so let's talk about the process structure. I'm going to focus on two processes in the system. So we have one process which I'm calling the analyst here, and it represents a single session of the analyst connected to the system, interacting with the system. So as an analyst, you open a page in the browser, and behind the scenes, some sort of WebSocket connection is established to the server, and this analyst process maintains that connection and interacts with the analyst on the other side. So it accepts incoming requests and sends outgoing responses. And whenever the analyst wants to run a query, the analyst process is going to spawn a query process, and this is where we're going to do our magic, fetch the data, do the processing, send the results to the analyst process, which then sends it over the wire to the other side, to the browser. Meanwhile, this query process stops, so these queries are ephemeral processes, temporary transient processes, dynamically started. And just by doing this separation, this simple separation, basically we are able to unblock a single analyst, so the analyst can interact with the system while a single query is running. So they can, for example, start additional queries as well, or do other kind of commands. And of course, by having a per analyst process means that a single analyst interaction with the system does not block other analysts working with the system. So other people can interact with the system, or multiple people can interact with the system in parallel, simultaneously, concurrently to each other. So that's the basic idea. This is one big important reason why we're splitting things into processes. So let's take a look at some code sketches. Basically, again, very low level code sketch, as many of you would have guessed, in production code, we would be using something called task to actually run this activity. But at the lowest level, basically, this is what happens. When I want to run a long running activity, I'm going to spawn a process, and I'm going to do my magic here. I'm going to run the query here, compute the results, send the result back to the analyst PID, and then this process stops. We execute the last instruction or the last expression, and then this query process stops normally. Now, an important point in this slide, I conveniently have hidden a lot of complexity behind this run query invocation. So a lot of stuff is taking place there. We're fetching the data. We're actually streaming the data because, it's too big to be fetched at once. And then we're processing the data as we go along. And so the boundness of this process is basically, it's kind of both IO and CPU bound somehow intertwined, because we're kind of having interlaced fetching from the database together with processing the data. But, we don't care about the boundness, unlike in some other technologies where you kind of have to figure out, like, is your activity IO bound or CPU bound? And depending on what the outcome is, then you're gonna either do like non-blocking IO, or you're gonna do some sort of, you're gonna use some sort of thread pool. We don't care in Beam, as we shouldn't care, because I really cannot know like what's the exact boundness or predominant boundness of some invocation, when it has a super large call stack, right? So I don't care. I want to run something independently from the rest of the system. I'm going to spawn a process. IO bound, CPU bound, combined, it doesn't really matter. It's going to run independently, and it's not going to block the rest of the system, nor will the rest of the system block this thing, right? So you have a single tool and you use it in all situations, which is like pretty convenient and pretty, I would say, much simpler than with many other technologies, where you kind of use multiple different tools to manage concurrency, like non-blocking IO with async await, thread pooling, microservices, and then you sprinkle some Kubernetes and whatnot, and it becomes like super complex pretty fast. Here we can really use a single primitive, for various kind of cases at all levels of abstractions. So either way, we spawn a query, and that's basically it. Now, I'm going to show you a couple of sketches related to the analyst process. So that analyst process, it's written in the style which we call server process. Essentially, it's the style or the pattern of how we write those processes. Again, a very low level sketch based on recursion. As many of you know, we don't do this directly. We use higher level abstractions, such as a thing called Gen server, for example, which make this thing more declarative. But the idea is always the same, So the server process basically loops for a longer amount of time, sometimes even, forever, indefinitely. In each step of the loop, it waits for a message. When the message arrives, it does something with the message, right? And this is what makes it a server process. And after, of course, it handles the message, it resumes the loop and waits for the next message. And that's what makes it a server process. It waits until the message arrives to serve it, to handle it, right? So basically, messages are requests here. It's a single-threaded server or sequential server. So processes are always sequential programs, right? So it handles one message at a time. And it may maintain some sort of state, some arbitrary piece of data, which changes over time, which may be transformed as we're handling each message. So this is like an abstract sketch of that of a server process. Let's take a look at some kind of a couple of examples of messages which are handled in the analyst server process. And so, just as an important point, like most of our processes are written in the server style, so we kind of do this kind of reactive event-driven concurrency, if you will. A lot of the processes are written in that style typically. So anyway, the analyst process, what kind of messages does it handle? So one message is going to be like, run me this query. So this message is produced simply by decoding the bytes that you receive from the other side, like via WebSocket or whatever connection you have. You somehow transform these bytes into this structured message, and then it's sent to the analyst process, and then we have like, run me this query. And so what does it mean to run a query? We're going to spawn a query process. And then we're going to take the PID of the spawned process, and we're going to store the PID in our own internal state, in the state of the analyst process. We're going to keep track of the processes we spawned, and then we're going to resume the loop, waiting for the next message, right? So that's basically it. It's a pretty fast interaction here, and the analyst process immediately becomes available, responsive for other messages. So another kind of message that we're going to receive would be the results sent from the query process. So typically this result is going to contain, at the very least, the PID of the query process itself, so we can identify who sent us the message, together with the actual results. And then what we do is we send the results to the other side, to the analyst, right? So we're going to encode it to JSON, send it over the wire. We're going to remove the query from our internal state, and then we're going to resume the loop waiting for the next message. And that's your happy path scenario. It's pretty straightforward stuff, nothing super complicated here. Now, we have to also deal with failures, with crashes, right? So things can go wrong. They will go wrong here. When we're running a single query. So for example, we may lose a database connection. We're streaming this data for like a longer amount of time, sometimes even more than an hour. So a connection might be dropped. We're doing some intensive post-processing, running some fancy complex algorithms. So we might have some bugs there, like, we end up with division by zero, square root of a negative number, and so on and so forth. So when such things happen, there's going to be an exception. And we typically don't handle exceptions. We kind of use this let it fail philosophy. So when an exception is not handled, the program will crash, just like any other program in any other language. But here the point is that, a single process will crash, not the entire Beam instance, right? This is what you have because you use this shared nothing concurrency approach. And so this is basically your kind of primitive or the tool for writing fault-tolerant systems. The idea is that the more aggressive we split our system into these independent or loosely dependent programs, processes, the less of negative effects will there be when single thing terminates or crashes, because these things are now very small and they have a fairly small role in the grand scheme of things. So the effect of losing them is not going to be very significant, And so this is how we mitigate or reduce negative effects of failures to the system. And then another side of the story is that although a crash is not a silent event, it's also not, although a crash is not an abrupt event, it's also not a silent event, which means that any other process in the system may be notified if it wants to. It may be notified that other processes have terminated, right? So basically, this is what we're going to use here in our analyst process, right? So we're basically, whenever we spawn a query, we're somehow going to ask the runtime, like, let me know if this query process stops. And then you're going to get the message, the process with the PID foo has terminated because of the reason bar. And then you can handle this message just like any other message. You can do something with it. So what are we going to do here? We're going to first, do a conditional logic on the reason. So there is a special termination reason called normal, which basically means that the process has run its course. We have executed all the instructions and the process has stopped normally. And in this case, we're not going to report anything because we already did that a few slides ago. Otherwise, if the termination reason is not normal, then it's abnormal, right? So something has gone wrong, and then we're going to report this crash. And typically, this reason will then contain like exception message together with the stack trace, so you can do like some fancy logging or whatnot. Either way, irrespective of the exit reason, this is the actual place where I would remove the query from the state. Not a few slides ago, as I've shown you, when I'm handling the result of the query, but here, because here I'm going to end up no matter how the process stops, normally or abnormally, right? So this is the single place where I'm going to remove the query from my own state, and then I'm going to resume the loop, waiting for the next message, and there you have it. We have handled, we have like proper crash or failure handling, error handling. And basically, this small example demonstrates what I believe is the philosophy of, splitting things concurrently in Beam, or splitting things into processes in Beam. Essentially, if we have two functions, foo and bar, and we wonder, like, do we need two processes for those two functions or one process? Basically, like, if you don't want a duration of foo to affect the duration of bar, and or you don't want a potential failure of foo to affect the outcome of bar, and or vice versa, then use two processes, else use one process, right? And so like any other things in life, this is a guideline, not a strict rule. So there will be occasional exceptions, but this is a very good baseline to start with, and it's really gonna serve you fine in the vast majority of cases in my experience. And it's pretty mechanical, you know, so it's not like it's more mechanical than art, unlike, for example, what I think about microservices, where it's kind of difficult to figure out the boundaries of your microservices. Like, should I run these things in separate microservices or the same microservice? Like, this is much, I find this much more straightforward to make a decision, like how do I split things across processes. Pretty mechanical in most cases. So that was a fairly simple example. Let's go into something a little bit more involved and hopefully more exciting. So the processing pipeline, right, and or the data ingestion pipeline, and this will be the case where Beam concurrency really shines, you know, where I think Beam languages are really a good fit. So the thing I'm going to discuss here, the actual use case is a small service that we have implemented as a part of a larger product. Which was, you know, ingesting the feed or various feeds, multiple feeds of or streams of events related to sport matches which are currently taking place, right? So like you have a bunch of matches like, I don't know, soccer, basketball, tennis, and so on and so forth, and they're taking place, and we connect to various third-party providers, and we accept stream of events describing different changes happening to those matches. Like, you know, there has been a change in the result, a goal has been scored, there is some attack taking place, you know, there has been a foul given, and so on and so forth. So we basically, you know, handle those events, and we maintain our own view of the world, our own model, the way we need to for the purpose of our product. And this is what our service does. And on each update to our model, we do two things. We have to make some updates to the database, which is used by other services in the system. And then we also have to send the updated model to another service, which I'm calling a server here. It's down at the bottom to the right, which is basically serving these data to the connected users. You know, so like when you connect to the web page of the product, you are getting your data from that server. So this is basically like your typical consume, process, and publish service. You know, if you've done some sort of event-driven services or microservices thing, especially based on Kafka, this is kind of done in that spirit, except there's no Kafka involved. And so, how do we implement this pipeline in Elixir or in Erlang, in a Beam language? How would we organize this into processes? It's basically this. You know, it's pretty straightforward. You know, this is what I like. It maps nicely to the stuff that we actually want to implement, right? So basically, I'm going to have like one process per each independent feed, and each of these processes is going to connect to the remote service. It's going to keep a network connection to the remote external service, and it's going to receive a stream of bytes, and it's going to convert those bytes into structured messages, which are then sent to the model process. And this is where everything converges. This is our point of synchronization, where I'm handling one incoming message, one incoming event at the time. And after each update to the model, I can update the database, and I can send the updated model to the server, and I can spread out. I can do this independently. I can do this concurrently, and hopefully in parallel, you know, because those are like independent actions. And again, you know, I don't care about the boundness. These processes have different boundness. So like the feed, for example, would be a combination of IO and CPU boundness. The model, pure CPU bound, database, primarily IO bound. Sending to the server is a combination of IO and CPU, because we have to encode to the JSON and then ship it over the wire, you know, but I don't care, always the same abstraction. And also, you know, all of these processes are implemented in the server style. So each process is basically, you know, running that loop, waiting for the message to arrive. Then when the message arrives, it does something, it handles the message, does its own processing, produces its own output, and then sends it as a message to the next process or processes in the chain. Now, this is the initial basic take, but as it turned out, you know, when we talk about the model, we can actually be much finer grained. The thing is, you know, the model is a collection of sport matches, and sport matches are completely independent of each other. And so rather than maintaining one big model, we can actually have per match model, and we can have per match process, so these things are started dynamically. Each match process is started when I receive the first message for that match, and then I keep somehow that process alive for as long as I'm receiving the messages for those matches, for that particular match. And so now I have like a potential for parallelism here, because basically, match or this processing of an event is pure CPU bound operations. So I can actually spread the processing across available CPU cores, and I can make my system vertically scalable. But even on a single core machine, there are going to be benefits, because handling of an event is done on a smaller active data set. And this is typically going to be faster, or much faster, because like we may have at peak times, I think, few hundred matches. And, clearly there's going to be like 2 orders of magnitude smaller active data set we're working on. This is particularly beneficial for garbage collection, because garbage collection in Beam is done on a per process level, not on the world level. We don't have stop the world GC. We have stop the process GC. So basically, when the process is actively running, when it's in the scheduler thread and some instructions are executing, if it needs more memory than it currently has allocated, prior to expanding its internal heap, it's going to be garbage collected, right? So we have like this garbage collection working on this smaller active data set, just one match rather than hundreds of them. And so it's clearly going to be much faster, and therefore we're going to have less interruptions, less unexpected latency spikes. Basically our GC becomes concurrent and distributed, spread out across times, and this preserves our latencies and makes our system more responsive. But most importantly, splitting matches into separate processes improves our fault tolerance, right? Because when there is a bug, it's confined to a single match. And this is a true story. There was a situation where there was like a subtle bug of, handling one particular message for one match. And basically, there would be an unhandled exception, and that particular match would crash. And, we weren't able to progress further with that match, because there was a bug. A human actually had to analyze the logs and fix the problem and deploy it. And it took some time, of course, until that happens. But in the meantime, only that match was affected. You have a much smaller surface of failure. So like out of, say, 100 matches, you still have 99 matches working completely fine. Most of your service is still preserved. And this is not perfect, but it's way better than nothing, and it's an example of how like splitting things concurrently can improve your fault tolerance, or make your system more resilient toward failures in the system. So anyway, one question that arises here when we have this process structure is, how will the feed process find the corresponding match process where it needs to forward the message, right? The incoming event. So basically it's a registry pattern, and I'm including it here as an example of how we do kind of an SOA, service-oriented patterns, directly in our language of choice at a much finer grained level. I would say that this is even finer than microservices approach. And how we don't need like to use etcd or something like that to make it happen. So basically, we're going to have one process which we call registry. It's going to be a server process, and the state of this process is going to basically be a map, keeping or maintaining the connection between the logical role of a process to its physical address, which is the PID, the process ID. Right. And so, of course, you don't have to implement this yourselves. You're going to use an off-the-shelf abstraction such as the registry module from the Elixir standard library. So either way, you're going to start this registry process someplace, and then when the match process starts, it's going to announce itself to the registry. It's going to like send a message. I am the process responsible for the match with the ID 123. And the registry stores this entry. And then on the other side, you have a feed process, which, reads an incoming event, and it reads some field from that event, like some sort of a match ID, and then it asks the registry like, who is the process responsible for the match with this ID? It gets the PID back, and then the feed process can interact directly with this match, you know. So pretty straightforward stuff. You know, just a couple of lines of code actually are going to be needed for that. Works, you know, like a charm. SOA pattern directly in your language of choice, which again, you know, demonstrates how we use like this single abstraction at different scales of thinking, you know, at a very low level or low level abstraction, as well as high level abstractions, you know, such as running those matches and having some registries in there. Either way, let's move forward. You know, one thing that I want to talk about here in the processing pipeline is how we are dispatching data to the remote server, right? So in a naive approach, you know, we have this dispatch process, which basically, you know, updates the new state of each match, and it ships them over the wire to the other side. So it has to encode to the JSON and then send it to the remote server, which is actually serving this data. Now, if you do this one message at a time, you know, you're going to actually fall behind the reality pretty quickly. Basically, you know, the problem here is that the networking is involved, and network can become unpredictable. It can become slower. You know, you can have like latencies of sometimes even a few hundred milliseconds when you're shipping something over the wire occasionally, and then you just fall behind the reality, even for fairly small incoming rate of messages. You know, we weren't really dealing with a lot of messages, to be clear. So like in normal times, we would be dealing with a few dozen messages per second, at peak times, few hundred messages per second. So this isn't low scale, but it isn't really high scale. You know, it's something like I would call intermediately loaded, moderately loaded system, right? And so either way, you know, sending or dispatching one message at a time is not a really good choice. Here, basically the solution here is to use batching, right? Because batching basically works because dealing with n things at once is way more efficient, way faster than n times dealing with a single thing. And this is typically the case when you have networking involved, right? And so if we do batching, you know, we're going to aggregate a couple of messages and then dispatch them at once, and then we're going to be way more efficient and more resilient towards network latency spikes and whatnot. So how do we do batching in the Beam language with these processes? You know, basically we're going to have another process here, which is going to be a batcher. So we have a batcher and a dispatcher. Basically, upstream processes, these batch processes are going to send the data to be dispatched to the batcher. The batcher aggregates this data and then periodically sends a batch to the dispatcher, which now encodes to the JSON, ships it over the wire. And meanwhile, concurrently and hopefully in parallel, the batcher may accept more batches and aggregate them and have them ready for the dispatcher, right? So that's the basic idea. The question is, you know, how frequently should we hand off the batch to the dispatcher? And so, you know, typically people here choose two parameters. They choose like some sort of a batch size, like I'm going to aggregate n messages. And then also they may choose some sort of cutoff time, like I'm going to wait, say, for m seconds before I hand off the batch, no matter how big it is, right? So the problem I have with this is that, like, if you pick those parameters, you know, which values should you pick? You know, it's kind of a question of picking some random numbers. And if those parameters are too small, you pick too small batch size or too small interval, then you're gonna have too small batches, and you might end up with the original problem of dispatching data too frequently, and therefore being susceptible to latency spikes. On the other hand, if those parameters are too large, then you're going to wait for a longer amount of time before you fully assemble the batch, and again you're going to introduce unwanted latency. So I don't go for those approaches at all. I tend to choose a different approach, which I call adaptive batching, which is kind of an example of demand-driven producer-consumer relationship. So I'm going to show you this. I'm going to zoom into this thing. So taking a look at this batcher and dispatcher processes, basically there is a producer-consumer relationship between them, batcher being the producer, dispatcher the consumer. And the way this is going to work is dispatcher is going to announce itself, it's going to inform the batcher that it is available, that it is idle, that it has room to take some work, right? So the dispatcher sends a message to the batcher, you know, I'm available, give me some work. And the batcher gives it whatever it has at that point, unless it has nothing, in which case the batcher is going to wait for the very first message to arrive, and then it's going to send this as a batch of one to the dispatcher, right? So the point is that as soon as something is available, it's going to send to the dispatcher if it's claimed, if the dispatcher says that it's available. So once the batch is sent, the dispatcher does its magic, encodes to JSON, ships over the wire. Meanwhile, the batcher accepts other messages. And once the dispatcher is done, it comes back to the batcher. I'm available again, give me more work. And the batcher sends it whatever it has at this point. And so the dance goes on and on. Now, the reason why this works fine is because it's basically adaptive, right? So if the messages arrive fairly infrequently and the dispatcher is fast, then basically you're going to end up with the batch of one, right? And it's going to work perfectly fine. There are not going to be any latency issues there. But if something changes, most often, the incoming rate of messages increases, but also maybe, your network may become slower occasionally because of some other reasons. What's going to happen is the batch size is going to automatically be increased to compensate for these new circumstances. So you're going to end up with a larger batch size automatically chosen. Once the circumstances clear up, the batch size is going to be reduced, right? And it's going to work perfectly fine. And the reason why I'm explaining this, why I'm talking about this, is to show like how this process or this message passing style concurrency helps me reason about those things. I was able to come up with this algorithm. It's definitely surely not something new, something I invented, but just coming up with it was pretty simple, pretty straightforward. Reasoning about the behavior of this is straightforward. I just draw a couple of boxes and some arrows between them denoting the messaging protocol, and I spend a few minutes thinking about this, pondering about it, maybe discussing with colleagues, and I can convince myself that whether this works or not, whether there are some loopholes there, when like reasoning about concurrency with this message passing, lightweight concurrency, and Sharednothing concurrency that we have at our disposal is super trivial, and it basically makes me feel smart. But the reality is that it actually helps me dump the problem down to the point where I can actually understand it and be able to hold it in my limited mind, right? Limited brain, right? And so this is why I'm a huge fan of Beam, especially Beam style concurrency. So the final scenario that I'm going to talk about, or the final feature, is the cancellation feature, right? So this is something which is surprisingly frequently, I would say, overlooked by various concurrency technologies, especially the ones trying to compete with the same in the same space as Beam, and also by the developers or by the users of those technologies. We tend to frequently ignore the fact that we don't just want the ability to easily start independent or concurrent programs. We also frequently need the ability to stop those programs. And this is what I'm calling cancellation here, right? So, for example, going back to that query execution in data analytics system, if you remember, we are running this long running query and we wanted to support the feature of canceling the query. The analyst has started the query and then they figure out oh, actually this query is not correct. I'm not going to wait for 1 hour until it finishes. I want to cancel it right now, and then I'm gonna want to start another query, right? So they hit the cancel button and this query should stop here and now. And so how do you do this in Beam? Basically, you have a runtime service, a runtime feature, please stop me this process. You invoke some function, pass it a PID, and the process is stopped. And there you have it, right? So what we're going to have in that analyst process, we're going to receive the request to cancel the query. And then we're going to look up in our internal state. So given some logical query ID, we're going to figure out what's the PID of that query. This is why we're keeping the track of the query processes that we've started. So we find the query process, and then we say process.exit, and we stop the process, right? So technically, this is called an exit signal, but the point is the process stops here and now, no questions asked, right? And this is completely, this is way easier, way simpler than in many other technologies, especially the ones based on CSP, such as Go, for example. The thing in CSP-based concurrency approaches, your concurrent activities or programs are anonymous. The communication channels have identities, but not the program themselves. And so, you cannot ask the runtime to stop the thing which you cannot name. And so you actually have to do a lot of improvisations manually yourselves. You have to devise some cancellation channel, which you pass as some sort of a cancellation token or as some sort of context throughout a bunch of functions. So like in this particular instance, this would be unfeasible. Running this query, as I said, it's a huge piece of functionality, very large call stack, bunch of functions involved here, and just passing, this cancellation token around, and then periodically checking, like, am I being canceled? Am I being canceled? Am I being canceled? And then unwinding the whole stack if I am being canceled. This is like, it's not really gonna work fine. So yeah, in Beam, you just ask the runtime, please stop me this process, and you're good to go. Now this shutdown thing that you see, it's called an exit reason, and basically, it's going to be included in the feedback message, which we are already handling. Like, this process has stopped with the reason full bar. So here we're going to get the reason that we specified, like the shutdown reason. And so now I know that here I'm handling the termination of the canceled or the terminated process, and I'm going to report it accordingly. And otherwise, I'm handling other cases such as, process crash and the normal termination, and that's basically it. Here we have like a pretty straightforward, simple cancellation. Now, we have, this is a pretty simple scenario, but frequently we need to also handle, or do some final cleanup in the process being terminated. We want the process to be able to drain its current work and to say maybe some last final words, to clean up the resources. And this is perfectly possible as well. So each process may ask the runtime, please convert me this exit signal into a message, right? And then this message basically goes to the end of your mailbox, to the end of your FIFO queue, so you can handle the messages that you've already received. And then when handling this message, right, so this is how you ask the runtime to convert the exit signal into a message. We call it trapping exits. So typically during the boot of the process, you're going to ask like, I want to trap exits, and then as a result, all exit signals are converted into messages. And then you're going to get this message like, you're receiving exit signal from this process with the reason full bar, and then you can basically do some cleanup here. Now, in many cases, for many things, you don't really need to do this. Like a lot of stuff is process oriented, owned by a process. So like memory is owned by the process, file handles, network sockets, and so on. So like when the process stops, no matter how it stops, normally or abnormally, those things are automatically cleaned up or reclaimed. But there are things like which Beam cannot keep track of, things specific to your application code. Like if a process creates a folder, then you're going to want to clean up this folder in this particular fashion, because the Beam cannot do this for you, right? So let's see a concrete example of that. And the final use case I'm gonna discuss is a custom implementation of a continuous integration, right? So as a course of developing our product, we, in one case, we basically implemented our CI in Elixir, not as CI as a product, but simply, hard-coded Elixir-driven CI for our main product. The reason why we did this, and I still believe that it's a good reason, is because basically, Elixir as a language, which is Turing complete, which has a pretty good integration with the underlying operating system, and which has rich support for massive concurrency, is a way more superior fit for CI than YAML. And I still stand by this belief. And from experience, this was by far the most enjoyable CI that I've had the pleasure of using or working with. So let's talk about some processes or the process structure of the CI. I'm going to describe the process hierarchy. So when I say hierarchy, there is no particular notion of process hierarchy in Beam, but there is like a logical notion in the actual application code or the abstractions that we use called OTP. The simplified version is, like there is always a first process which is started, and we would call this process like the top level or the root process. And that process is going to spawn some other processes, which would be like the logical children of that root process, and then those children are going to spawn their own children, and so on and so forth. And this is what we call a process hierarchy. I like to think of it as a sort of a top-down view of the activities in our system, a top-down service manager, system D, if you will. And so let's take a look at some processes in this CI system. So, we have like the root process, CI, and then the main thing that we have underneath are the builds. These are dynamically started processes. So basically a build is a single execution of a CI Like, I push something to the main branch, we're running one build. You push something to your own feature branch, you're running another build, and so on and so forth. And so what we can see from this diagram, that these things are running concurrently to each other and then hopefully in parallel as well. Now, a single build is further subdivided into projects. So basically, our product was organized as a service-oriented thing, not microservices, but it was split into a couple of different services deployed separately to different targets. But it was organized as a mono repo because I believe that this is the way for the vast majority of cases. So we had like one repo where all of these services were residing, and so we would have to be building multiple projects, right? And so what we see here is that we have concurrency on a per project level. So again, more potential for running things separately, independently, hopefully in parallel. And as a sort of demonstration of what kind of benefits you can reap when you own your own CI, we wouldn't be always building all the projects on every commit. We would actually do a git diff between the last cached state and the new state, and then we would be able to figure out, which projects have to be rebuilt. And typically it was just like one or two projects in the vast majority of cases, which significantly, reduced the running time of our CI, right? And so this is something which is typically, difficult, if not impossible, to do with YAML-driven CIs. So either way, building a single project is further subdivided into processes. Basically, building a project means running a bunch of commands, like, fetch me the dependencies, compile the project, run some tests, run the linter checks, and so on and so forth. Each command would be running in its own process, and we will be running all those things in Docker container. And what we can see from this diagram, that basically, we have one process per each Docker container. So when I start the process, it's going to start the Docker container, and also per each command that I'm running. So when I run the command, I actually start the process, which starts the command, and the process, the lifetimes of the process and the command itself are tied together, are coupled completely. And what you can see from this diagram, that even at the command level, we have concurrency or parallelism, if you will. So it was like perfectly possible to run, for example, tests and linter checks concurrently, independently, which of course, again, reduces the execution time and also allows us to report multiple failures of multiple checks in a single round trip, in a single CI execution. Okay, so either way, the challenge here is now canceling a single build. This is a frequent challenge in a CI because basically, when you push something, if you had like the previous instance of the build running, you want to stop that instance before you start the new one. So this happens frequently. I do some coding, push to the main branch or to my feature branch, for example, then I figure out, oh, this is wrong, I'm going to do some fix up, and then I'm going to push something else, and then I want to stop the previous build, before I start the new one. And so what we have to do is we want to stop this whole process structure, right, before we start the new one. If we don't do that, then we might end up with some race conditions, with some weird bugs, or at the very least, the previous execution, which we don't need anymore, is going to, consume our resources and make everything slower, right? So we want to stop this thing. So to do this, we need to implement custom termination logic in each process. Each of these processes is going to be a server process, and each is going to have its own custom termination logic. So the processes which are parents, which have their own process children, basically have to stop when they are being terminated. They have to stop their children before they stop themselves, and they have to stop the children in the opposite order of the startup order, because typically younger children may depend on their older siblings, right? So this is what you need to do, but you don't need to do this yourselves manually. Essentially, you have to use the right abstraction, which is typically the thing called supervisor from the OTP, to make it happen. And so it's going to be like, you just properly organize your supervision tree or your process hierarchy, and this is just going to work out of the box, And so if you do that, basically, you're just going to have to ask the top level process, like the build process, to stop. And behind the scene, what's going to happen, the logic is going to recursively walk or descend to the bottom, to the right, and then unwind, stop in one process at a time synchronously. And then, your entire subtree is terminated properly without any dangling processes. And so then the only thing that you have to do manually, you're going to have to implement your termination logic in the command process and in the container process. So each of these processes basically starts an external resource, like an OS process. And basically what you want to do is when they are being terminated, a command process should like kill the corresponding OS process or send a sig term or something before it stops itself. And the container process should stop the Docker container before it stops itself. And once you do that, canceling a single build basically boils down to sending an exit signal to the build process. And then what we do is we wait for the confirmation message that the process has been stopped. And so once I receive that message, I know that build is not running anymore, that none of the activities started by the build are running. So the build is completely cleaned up, and I can, do something else. I can report like the build has been canceled, and I can start another build, for example, in its place. And even this, you don't have to, code manually. You're going to use some abstraction, like some sort of a stop function from some module to make it work. So that's basically it. That's all I had for you. In summary, you have seen a couple of different scenarios where Beam concurrency can be used. I would say it's pretty versatile stuff. And you have seen it at different levels of thinking of abstraction, right? So like very low level, very fine level of granularity, as well as sort of high level of organizing our system at large, at the macro level, if you will, especially in this CI thing as an example. And we always use the single tool. We don't care about the boundness. Pretty powerful, does exactly what we are supposed to or what we wanted to do. So there's like less stuff to learn, and you can achieve a lot of things, a lot of desired functionality with a single tool that you learn, which is what I like about Beam. And I have barely scratched the surface of concurrency examples. So you can take a look at some other talks that I gave. So for example, this one, which is also a virtual talk given a few years ago at Yao Lambda Jam, it's basically, the style of the talk is the same as this talk, but the examples are completely different. So they use, there I use like examples more in the context of your typical web server. So you may want to check that out. And then there's a talk called The Soul of Erlang and Elixir, in which I explore properties of Beam concurrency, like the basic features in more details. It's a demo-driven exploration. So I think it kind of makes those ideas and those principles that we have at the foundational level hopefully more tangible. And so basically that's it. That's all I had prepared for you. So I want to thank you for your time, for your attention, and I'm now ready to take questions.
Awesome. Thanks so much, Saša. What we might do is might just ask people in person here at the venue. Does anyone have any questions they'd like to ask Saša? Yep, go ahead.
First of all, thanks a lot for the talk. So I'm quite new to this ecosystem, so my questions might be too naive or too silly. So I got a few questions here. The first one is, what are the benefits of using this Beam architecture or this Beam approach? Are we using the messaging queue or using Kafka, like you mentioned before, or using AWS serverless services to build this, I don't know, application? That's my first one. The second question is, when the message or the process fail to execute, how can we replay it? And the third one is how to debug this process.
Okay, so let me start with the first question. I'm actually you still see my screen, right?
Yes.
Okay, so I'm actually gonna head down to, let me find it. Where is this? The books, blah blah blah, Elixir in Action. So this is my own book, and I'm gonna do a little bit of so there it is. This is the famous table which occasionally makes the round, and what we see here basically discusses like two real systems which I was working on side by side. It's like been more than 10 or about 10 years ago now, and so we have a bunch of what you see here in this column. We have a bunch of technical requirements that we have to do, like we have to serve requests, we have to do the processing and so on and so forth. And so the first system is more conventionally built, like, you know, like how you would typically build. So that one was the main language was Ruby on Rails, and we used a bunch of other stuff. And you can see a bunch of different technologies used, you know, very heterogeneous, organized. System B has the same technical functionalities. You know, it's not as complex as a System A, but in some cases it's actually more demanding. So for example, on the terms of scale, it was actually operating on a larger scale, a single piece of technology used, and it was organized as a single project, you know, deployed in a single place. And so the point here is that, like, the point is that this is a much simpler approach. You know, there are less moving pieces compared to your traditional approach with like external components like Kafka, for example, and whatnot. Obviously, you know, when you have less moving pieces, you have less operational complexity. You know, there are less stuff to learn. You basically learn just Beam style concurrency with, of course, associated abstractions in Beam. But you know, that's kind of, I would find, easier to learn within the context of a single language rather than, you know, when you're having to do with a bunch of completely different technologies. I think that these are kind of the main benefits, and this is actually the reason why I completely fell for Beam languages. In that instance, it was Erlang even before I discovered Elixir. So that's being said, of course, that, you know, this stuff in Erlang is not gonna completely match these full-blown third-party products, you know, such as Kafka, for example, or database such as Postgres and whatnot. But in many instances, what I have found, and I frequently talk about this, you know, make this point, is that, like, us people working with Elixir or with Beam languages, we have to much less frequently reach for third-party products, for external products, you know, than compared to many other languages, even languages with massive concurrency, such as Go, for example, right? And as a result of this, the overall architecture of the system is simplified, you know, to work with both for developers and operation people. So that's the question number one. The question number two was the process crashes. So how do we replay it and how do we debug it? Basically, let's go for debugging first. So when the process crashes, it's gonna be logged. The crash is going to be logged. It's gonna contain like the crash reason and the stack trace, and so you use that, you know, to figure out what went wrong. When it comes to replaying the crashed work, so as I said, at the lowest level of abstraction, each process can react to failure of other processes. So when a process crashes, some other process may restart it, right? And so we actually do have the abstraction for this, which is called supervisor. It's frequently used. Basically, you know, the supervisor is going to restart your process, and then you can kind of retry the work, and it actually can work in many cases. You know, because the theory is that sometimes, you know, bugs may occur simply because there is some kind of intermediate constellation in the entire system, which kind of prevents the thing from running well, you know. So sometimes restart helps, and you can actually organize this or do this with supervisors to, you know, restart the process and basically try again. This is, you know, again, essentially your service-oriented architecture, but implemented directly in Beam. And this is another thing which I like, you know, tying back to the first part of the question, or the first question, is that, you know, I have to deal less with systemd or with, say, Kubernetes, you know, organizing the dependencies between my services and then restart frequencies and whatnot. I can do all of this directly in my language of choice, or most of this work directly in my language of choice, which again makes, you know, my work uniform. It requires less stuff for me to learn. It's easier to onboard people to such solution, you know, and has less moving pieces. Yeah, so that's basically, that would be the answer. I hope that this answers the question.
Yes, thank you.
Should we take a question maybe from someone who's joining us online? Does anyone have one? If so, raise your virtual hand so I can see you. If not, we'll revert back to in person. Oh, Rob, feel free to unmute yourself and ask a question.
Thank you. Thanks, Saša. My question is about the I guess the rise of NIFs in natively implemented functions for anyone who's not sure about that term, especially now that things like Rustler and Ziegler exist, which make it really easy. And how do you see that impacting concurrency or guarantees we have around concurrency as more and more libraries in Elixir are using Rustler or Ziegler or what have you to talk to native packages?
Yeah, so this is an interesting question, which kind of opens up a potential for the whole talk, right? So just to clarify for those who are maybe new to this whole ecosystem, NIF basically means the ability to run native code in Beam. Like, for example, code written in C, clearly it's done for, or it's used typically for performance reasons because it's going to be way faster than running some sort of managed code. But it's also what I like to describe as a backdoor around the abstraction, because, when you run in process C, then, all the guarantees are off, right? So you can crash the entire Beam, or you can, skew the scheduler workings to the point where the concurrency kind of doesn't work as you'd expect it to. Now, there has been a lot of improvements in this area in the past decade, especially in the past 5 years, I would say. So we have gotten something called dirty schedulers, which helps with the scheduling, with how NIF code can affect scheduling. And then, as you mentioned, we have safer languages such as Rust, for example, and we have like a bridge with Rustler to integrate code written in Rust rather than in C. So this code is way less likely to crash and therefore crash the entire Beam instance or the entire system, right? And so I think that we are like now at an interesting point where writing NIFs becomes easier because we can use like some somewhat higher level languages than C, and also it becomes safer. So I think that it's definitely way better than it used to be. But either way, running in-process code is always going to be backdoor around the abstraction, and even with all the new improved guarantees and safetiness, it's still not going to be completely bulletproof. But there is another thing which is frequently my first choice when I want to run external code, which is called port. So port basically allows you to start a program written in any language from Beam. And basically this program communicates with Beam via standard input-output or via the I/O pipes in a message passing fashion. And this is pretty straightforward to do. In case someone is interested, you can take a look at the blog post I wrote. It's called, let me find. So my blog is called The Erlangelist, and then this post is called Outside Elixir. It has an example in Ruby, a bunch of code snippets about this. And so this is my favorite way of running external code. It's not as definitely not as fast as NIF, but it's way safer and it basically preserves the abstraction. And, I tend to reach for this approach first. But either way, the NIF story is definitely way more interesting and way more usable, way less dangerous than it used to be, like say 10 years ago when I started, or a bit more than 10 years ago when I started working with Erlang, right? So that's really exciting.
Thanks very much.
We've got any more questions from the audience in person? No? Cool. All right, pass the baton back to online. Anyone else with any final questions? Scott.
Hi guys, hope you can hear me. Thank you, Saša. It was a really good talk. I just thought maybe, I don't know if it was worth commenting on like the messages that you're passing between processes and their sizes, and because I know if it's just like a small message, it's basically the message just gets copied from one process heap to the other process heap. But when there's big binaries, my understanding is it uses a sort of global heap or something. Is when we're sending big binaries, I don't know, can you sort of comment on how that might impact performance or if it improves performance maybe?
So yeah, message passing. This is an interesting story. Again, probably one could do an entire talk. Maybe not 45 minutes, but something like that. Long story short, messages are typically, in most cases, as you said, copied between processes, right? So the content is deeply copied in most cases. They actually have experimented with using like the shared heap, but this failed spectacularly from what I've read. This was something like, I think, more than 10 years ago or so. The reason why this works well, this copying is because, you have like true independence through shared nothing concurrency, and then processes can be separately garbage collected, right? So this is your game. Now, some messages or some types of data are not deeply copied. The most notable example are big binaries, so big binary chunk of data. This also includes string, which is, just shared and reference counted. This is, of course, then going to work much faster. Otherwise, it's simply about carefully choosing your protocol, so you don't want to have like overly chatty processes, and you definitely don't want to send too much data. It's fine if you like occasionally send some large message between processes, because it's an in-memory operation, so it's going to be copying is going to be pretty fast, even if for very large messages. But you just don't want to do this like in a tight loop, where like you have like a very tight loop and you send a large payload between two processes. This is really going to hurt you then. But otherwise, it's about just choosing your message protocols. And this is another example of how we basically are dealing with service-oriented kind of thinking, or distributed thinking from the day one. And that's in a good way. It kind of helps you organize your system in a sort of nice way of, or nice collection of independent or loosely dependent programs, which are decoupled by with a solid message protocol, and then it makes it more straightforward. It's never easy, but it's more straightforward to go fully distributed to run your system across multiple machines, which of course Beam also supports. So I didn't even touch on that, but basically this message passing works not just across processes within a single Beam instance, but also across processes between multiple Beam instances, possibly running or typically running on different machines. So you have to think a little bit about your protocol. Don't be overly chatty, but otherwise, in most cases, really, this message passing, or the fact that the message is copied, is not a problem if you design your protocol well. Stay clear of synthetic benchmarks, which tend to like pass something around the ring and then compare different languages, and then typically, Beam languages don't come out on top of that. But this is really completely synthetic, taken out of any context, and doesn't really consider, what kind of gains do you get because messages are being copied rather than shared on some sort of heap. I hope that answers your question. If not, feel free to ask further.
No, that was perfect. Yeah, just getting an overview was really good. Thank you.